This video will explore the two hidden failure modes of ferrite beads and how DC bias and LC resonance can silently sabotage your power supply filter. We will also cover how to prevent these issues. Ferrite beads are a popular passive device for filtering high-frequency noise on power rails. They are designed to act as a resistor at high frequencies, dissipating noise energy as heat in a simple low-pass filter setup. To understand failures, we must first understand the bead's RLC model. Its behavior is defined by three regions: inductive, resistive, and capacitive. Effective filtering relies on operating within the resistive region for noise dissipation. Pitfall number 1 is DC bias current. Datasheets specify impedance at 0 DC bias, but load current is never 0. The DC current saturates the ferrite core, collapsing the bead's inductance and destroying its filtering ability. The current rating is a thermal limit, not an operational one. As DC bias increases, the core saturates and inductance plummets. Evidence shows inductance can collapse by up to 90% at half the rated current. The loss of inductance causes a catastrophic drop in impedance across the effective frequency range. The component effectively stops working as a filter when you need it most, as shown by these impedance versus frequency plots. A key design rule is to operate beads at about 20% of their rated DC current for effective noise filtering. Operating at a fraction of the rating preserves the core's magnetic properties and maintains the bead's impedance. Pitfall number 2 is that your low-pass filter can become a high-gain amplifier. Combining a ferrite bead with a high-Q ceramic decoupling capacitor creates an LC tank circuit that will resonate, amplifying ripple and noise. When the LC resonant frequency is below the bead's crossover frequency, peaking occurs. This can result in an unwanted gain, such as 10 decibels at 2.5 megahertz, amplifying noise instead of attenuating it. In a case study with an ADP5071 regulator, an undamped filter's resonant peak landed on the regulator's switching frequency, amplifying the ripple by 10 decibels instead of attenuating it. This worsens the noise. To prevent resonant peaking, we must add resistance to the LC tank circuit to lower its Q factor. This process is called damping. We will evaluate 3 common damping methods. Comparing the damping methods, Method C provides optimal performance. It eliminates the resonant peak without compromising high-frequency filtering, unlike the other methods which introduce trade-offs. The most elegant solution is Method C, a damped RC network. This network effectively dampens the resonance without degrading high-frequency performance by adding a large capacitor in series with a small damping resistor. Implementing Method C on the ADP5071 successfully eliminates the resonant peak. The 10 decibels gain is eliminated, and the 2.4 megahertz ripple is now reduced by 5 decibels relative to the no-filter baseline. Remember these 4 rules for using ferrite beads correctly. Acknowledge the true RLC model. Respect DC bias by operating at 20% of the rating. Anticipate LC resonance, and damp by default, preferably using Method C.